External direct product. Definition. Let G1 and so on Gn be a finite collection of groups. The external direct product of these groups is written this way, and is the set of all antiples for which the ith component is an element of Gi, and the operation is component-wise. This external direct product is just the set of all antiples when Gi is in the group Gi. And these two antiples, the product is defined to be G1, G1 prime, comma, G2, G2 prime, and so on, comma, Gn, Gn prime. This product is computed in the group Gn. If R is the additive group of the real numbers, then R squared is R external direct product with R. This is just the plane. We add pairs component-wise, which correspond to adding vectors in the plane. Example 1. The external direct product of the groups U8 and U10 is this set of pairs. U8 has the numbers from 1 to 7. All the odd numbers are relatively prime with 8. And these are the entries, the first entries, 1, 3, 5, and 7. And the second entries come from U10. These are the odd numbers, 1, 3, 7, and 9. Because the odd number 5 is not relatively prime with 10. And the operation here will be multiplication, because the operations in U8 and U10 are multiplications. We multiply these pairs component-wise. 3 times 7, 21, mod 8, it is 5. And 7 times 9 is 63, mod 10, it is just 3. Example 2. Z2 external direct product with Z3 is the set of these pairs. We know that Z2 has 2 elements, 0 and 1. Z3 has 3 elements, 0, 1, and 2. 0, 1, 2. These are the second entries, and the first entries of pairs are zeros and ones. And we have altogether 2 times 3, 6 pairs. We'll see that this group is isomorphic to Z6. Consider the pair 1, 1, this pair, and find all multiples of 1, 1. 2 times 1, 1 is 0, 2. This is just 1, 1 plus 1, 1. So we end up with this. And we continue this way. And you see that 6 times 1, 1 is 0, 0. And this is for the first time we get 0, 0. Which shows that the order of the pair 1, 1 is 6. And since we have an element of order 6, the pair 1, 1, it generates the whole group. So it is, and the group is cyclics of order 6. And that's why it is isomorphic to Z6. The group Z2 plus Z2 is order 4, but 1, 1, the pair 1, 1, has order 2. And any non-zero pair has order 2. So this group Z2 external direct product with Z2 is not cyclic. It is not isomorphic to Z4. We see that when we have Zm external direct product with Zn, it can be isomorphic to Zmn, like in example 2, and it may be not isomorphic to such group. Our first theorem gives a simple method for computing the order of an element in a direct product in terms of the orders of the components pieces. The order of an element in a direct product of a finite number of finite groups is the least common multiple of the orders of the components of the elements. It is written symbolically, it is this: the order of the pair is the LCM of the order of the components. Proof: let EI be the identity of the group GI, and let S be the LCM of the order of G1 and so on, the order of Gn. And let T be the order of the n-tuple. Because S is a multiple of each order of elements, it follows that the n-tuple to the power S, which is this, is equal to E1, E2, and so on, En, because S is a multiple of the order of Gi. This shows that S is bigger than or equal to T, because T is the order of the n-tuple. On the other hand, from G1 to the power T and so on, Gn to the power T equals the pair, the n-tuple to the power T equals E1 and so on, En. It follows that G1 to the power T is equal to E1, and this means that the order of G1 divides T, similarly the order of G2 divides T, and so on, the order of Gn divides T. It follows that T is a common multiple of all these orders. That's why S is less than or equal to T. From these two opposite inequalities, we conclude that S and T are equal, and this proves the theorem. Example 4. All these groups listed here have order 100, and in direct product, the order of the group is equal to the product of the orders of the components. So Z25 has 25 elements, Z2 has 2 elements, 25 times 2 times 2 is 100, and Z100 is also a group of order 100. 5 times 5 times 4 is also 100. 5 times 5 times 2 times 2 is 100. This is the dihedral group. D50 has order 2 times 50, 100. And we know that it is not abelian, so it is not isomorphic to either of those listed before, because each of the previous groups each of them is non-abelian. Here, D10 plus Z5, this external direct product is of order 20 times 5, again 100. And we can see that, say, the first two groups are not isomorphic because this is cyclic. There is an element of order 100, and here we have triples. The order of 1, 1, 1 is the LCM of 25, 2, and 2, and the LCM of 25, 2, 2 is 50. So this is the largest possible order in this group, Z25 plus Z2 plus Z2. So it is not isomorphic to Z100. Example 5. Determine the number of elements of order 5 in Z25 plus Z5. We have to determine the number of pairs AB such that the order of the pair is 5, and from the previous theorem, the order of the pair is the LCM of the order of A and the order of B. So either the order of A is 5 and the order of B is 1 or 5, or the order of B is 5 and the order of A is 1 or 5. Only then we have this equality. We consider two mutually exclusive cases. In case 1, the order of A is 5, the order of B is 1 or 5. There are 4 choices for A. Say A is either 5, 10, 15, or 20, and 5 choices for B. B can be any element of Z5. So altogether, we have 20. 4 times 5, 20 elements of order 5 is in case 1. In case 2, we consider the order of A to be 1 and the order of B to be 5. This time, we have one choice for A must be 0, and we have 4 choices for B, any non-zero element of Z5. This so we have obtained 4 choices for altogether 4 choices for case 2, and altogether we have 24 elements of order 5.